We know the procedure to solve the Laplace equation, but how does this work in practice? In this video you will see an example, and as you will notice we can follow the same approach as in the case of the heat equation and the wave equation. Solutions will look differently though, as you will find out by the end of this video. So we are solving the Laplace equation in 2D in a rectangular domain. So Laplacian u equals 0, x is between 0 and a, and y is between 0 and b, where a and b are some parameters. Then we set u to 0 on y equals 0 and y equals b. So there we set it to 0. And we set u to 0 on the left, where x equals 0. And we set some function for u on the right, some f of y. And by the end of the video, we need some explicit f of y, so I took an easy one. I just took 1. So it doesn't really matter what it is for the whole procedure, but for the final calculations, it's convenient to put an easy one over here. So I put 1. So what do? Now, first of all, we use separation of variables. We will look for solutions of the form un of x and y equals x of x times y of y. Then un xx equals xx and y, and un, yy will be x times yy. Then we substitute this into our Laplace equation over there. We get xxy plus xyy equals 0. We separate, we divide by x times y. We get xx over x equals minus yy over y. The left-hand side only depends on x. The right-hand side depends only on y, which means that xx over x is a constant, lambda equals minus yy over y. Furthermore, we look at the boundary conditions. Un of x, 0 equals xx times y of 0 has to be equal to 0. So that means if we want to if this needs to hold for all x, this means that y of 0 equals 0. And similarly at y equals b, so you have y of 0 equals 0 and y at b equals 0. That will give you a boundary value problem for y of y. So we have here y equals minus lambda times y, that's over here. We have y at 0 equals 0 and y b equals 0. Well, you have by now already encountered this boundary value problem probably a lot of times in the heat equation, the wave equation. So you know, in principle, you have to look for lambda 0, lambda negative, lambda positive. But in this case, you will only find non-trivial solutions if lambda is positive. So we put lambda equals mu squared. You get y of y equals c1 times cosine mu I plus c2 times the sine of mu y. Due to this boundary condition, the cosines drop out, so you are left with c2 times the sine of mu y. And in order to satisfy the second boundary condition over here, you need the sine of mu times b to be equal to 0. So mu times b has to be a multiple of pi, and we denote our solutions as sine of mu times y, so that will be sine of n pi y over b. And our lambda will be equal to mu squared equals n pi over b squared. So, end of this step, we have found y of y. Moving on to x of x. Now, x of x equals lambda times x. So there we go. So xxx is some positive constant times x. So you get exponential functions. X of x equals exponent plus mu x and exponent minus mu x. Now it's convenient to use here the cosine hyperbolic and the sine hyperbolic instead. So cosine hyperbolic is of x equals ex plus e minus x over 2, and sine hyperbolic equals x minus e minus x over 2. So it's convenient to use these combinations instead of the pure exponentials, as you will see in the next step. So our x of x equals a times the cosine hyperbolic plus b times the sine hyperbolic. Now we plug it into our u of x and y. So we get sum, and from 1 to infinity, the y of y times the x of x. Then we use our first boundary condition, and that's where the hyperbolic functions shine. U 0, y equals 0. Because if x is 0, the sine hyperbolics drop out and the cosine hyperbolic equals 1. So you only have an sine n pi y over b has to be equal to 0. So you immediately have that your an's are 0. Then you are left with your second boundary condition. a comma y equals now only the bn times sine n pi y over b times sine hyperbolic n pi a over b. And notice, by the way, that this over here, the scalar rooting thing, is just a number. That has to be equal to f of y. And now if you want to proceed, if you want to compute your bn, you have to specify some f of y, and this in this example I just took 1. So what do we want? We want to express our f of y as a sum of sines. So we have to write our f of y as a Fourier sine series. Now, how do we do this? We need a Fourier sine series of f of y. So our f of y can only have sines. So we have to make the odd periodic extension. And then we know our odd periodic extension can be written like this, with a small bn sine, bn times the sines. And we know how to find these bn's. They are 1 over 2b integrated from minus b to b, the f odd times the sine. Then we know f odd is odd, the sine is odd, so the integral from minus b to 0 equals the integral from 0 to b. So this integral equals twice the integral from 0 to b. So you have 1 over b, integral from 0 to b of f odd times the sine. Now we have the same trick as always. On 0b, f odd is the same as f. So we can replace our integral by 1 over b integral from 0 to b f of y sine n pi y over b. Now this is still all for a general f of y. Now in this particular example we put f of y equals 1. So if you have another f of y, you just get another integrand here. So we're left with this integrand to compute our coefficients bn. Well, that's an easy integral. So 1 over b times this integral, sine n pi y over b gives you a cosine. Between the boundaries, plugging in the boundaries, you get your integral over here, 1 over n pi times 1 minus cosine n pi. So your f of y can be written as a sine series like this, by plugging this in over there. Now we return to our original u at a comma y, that was this one, and has to be equal to f of y. Now we compare both theories, we compare the terms, we have the signs here, so the sine n pi y are the same, so that means their coefficients have to be the same. That means that bn times the sine hyperbolic has to be equal to this coefficient over here. So the bn times the sine hyperbolic has to be equal to 1 over n pi times 1 minus cosine n pi. And now we can solve finally for our bn. So our bn just divide by the sine hyperbolic. So the bn is a bit awkward over here, but it's just a coefficient depending on n and a couple of parameters. That's what you can plug in into your u of x and y. So here there's the bn go. Here we have the sine n pi y over b, and here the sine hyperbolic n pi x over b. And there you have the solution of your Laplace equation. And notice that this really looks a bit different than the solutions of like the heat equation and the wave equation, which you have seen before.